Section: Introduction. In this section, we discuss the advancements in generative methods, particularly focusing on diffusion techniques, which are currently leading the way in creating media content like images and videos. A significant breakthrough was the introduction of the diffusion transformer, first proposed for image generation, which outperformed the previously popular U-Net models and demonstrated better scalability. We also highlight the concept of latent diffusion, where the diffusion process works on compressed representations of images or videos, making it more efficient, especially for video generation. Diffusion transformers can be divided into two main types, cross-DIT and MMDIT. The main difference between them is how they handle text and visual information. Cross-DIT processes text and visual tokens separately, while MMDIT does so in parallel, which may affect how attention matrices are structured. The potential of transformers in latent diffusion for video generation was first shown by a closed-source solution called Sora. Since then, many other solutions, both closed and open source, have emerged, but they often share a common issue: they rely on computationally expensive full attention mechanisms. Recent studies have shown that attention matrices can be sparse, indicating opportunities for improving computational efficiency through sparse attention methods. We categorize methods for simplifying attention mechanisms based on two features: dynamism and usage scenario. Dynamism refers to whether attention patterns are identified statically or dynamically, while usage scenario indicates if the method can be applied in a zero-shot manner or requires training. Traditional static patterns include sliding window attention in NLP and window-based attention in computer vision. Newer methods like neighbor attention have emerged, which use overlapping windows for better efficiency. While static patterns leverage empirical knowledge about data structures, they may not always align with the patterns learned by transformers during training. Research has shown that attention masks can vary significantly across different blocks, heads, and even during various stages of video generation. Some methods focus on dynamically selecting attention patterns, while others, like ADA-SPA, use online searches to find suitable block attention masks. We note that while many studies have explored sparse attention in NLP, the application to video generation is still evolving. We present NABLA, a neighborhood adaptive block-level attention method that simplifies the process by using a downsampling approach instead of requiring additional training. NABLA adapts the sparsity mask dynamically for accurate attention calculations. Our key contributions include efficient threshold selection for adaptive masks, which outperforms fixed sparse patterns, and compatibility with existing acceleration techniques. We also ensure a straightforward implementation without the need for custom CUDA kernels. Our evaluations on video datasets show that NABLA achieves a significant speed-up while maintaining comparable performance metrics, demonstrating its effectiveness in both inference and training of diffusion models. Section Summary. In this section, we discuss the advancements in diffusion methods for media generation, particularly highlighting the diffusion transformer and its variants, cross-DIT and MMDIT, which improve upon traditional architectures. We introduce NABLA, a novel approach that optimizes attention mechanisms for video generation by dynamically adjusting sparsity masks, achieving significant speed improvements while maintaining performance metrics. Section: Background. In this section, we discuss the background of attention mechanisms in the visual domain. The classical self-attention mechanism, introduced in a key paper, transformed deep learning by allowing dynamic focus on important parts of input data through interactions between tokens. In visual tasks, this mechanism processes images and videos by breaking them into smaller patches and mapping them into an embedding space. For an input sequence represented as a matrix, we project these tokens into queries, keys, and values using learnable weight matrices. We calculate attention scores by taking the dot product of queries and keys, followed by a softmax operation to create an attention matrix. Each entry in this matrix indicates how much one token influences another. For video diffusion transformers, the input consists of spatiotemporal tokens, where the number of tokens can grow significantly with high-resolution or long-duration videos. This leads to challenges due to the quadratic complexity of the self-attention mechanism, which can become computationally expensive. Many attention weights are often close to zero, resulting in unnecessary calculations. To overcome the limitations of full attention in video generation, we introduced sliding tile attention, STA, which is a more efficient alternative that takes advantage of the 3D locality in pre-trained video models. STA organizes the input video into non-overlapping tiles that match GPU block sizes. It computes attention only between query and key tiles within a fixed 3D window, reducing redundant computations and improving efficiency. By aligning tile sizes with GPU thread blocks, STA achieves significant speedups while maintaining quality. However, STA's static window partitioning may not fully capture dynamic content, requiring careful tuning to avoid visual artifacts. During our experiments with STA, we noticed a significant issue of object duplication in high-resolution and long video sequences, which we attributed to insufficient global attention coverage. We hypothesized that an effective sparse attention algorithm should maintain long-range dependencies, but the complexity of these dependencies makes them hard to capture with fixed patterns. While Santa offers efficiency through hardware-aware sparsity, its static nature limits its adaptability to different video content. To address these challenges, we propose NABLA, which learns context-aware sparsity patterns to ensure global coherence. NABLA uses downsampled full attention to dynamically select the most valuable blocks for each attention head. However, we also found that adaptive sparsity can introduce artifacts, such as visible borders between areas recovered from neighboring pixels. To mitigate this, we combine NABLA with STA, achieving a balance between computational efficiency and high-quality generation, thus addressing the limitations of both static and dynamic approaches. Section Summary. In this section, we discuss the limitations of classical self-attention mechanisms in video generation, particularly their quadratic complexity and issues with object duplication in high-resolution outputs. We propose NABLA, an adaptive sparsity algorithm that learns context-aware attention patterns, and combine it with sliding tile attention, STA, to achieve both computational efficiency and high-quality video generation. Section: Training Algorithm. In this section, we present a training version of the NABLA algorithm. We emphasize the importance of token reordering, which helps establish semantic connections between adjacent tokens, following the approach of Santa. Our method uses fractal flattening with spatial patches of size p by p, grouping all tokens in each patch into a continuous sequence of p-squared tokens, while keeping the original order in the time dimension. We apply this reordering at the input stage of the DIT network and reverse it at the output stage to maintain spatial relationships and computational efficiency. Next, we describe the NABLA mask computation algorithm for multi-head self-attention. This algorithm takes input data represented by queries and keys, each containing S tokens of dimension d. We denote the number of transformer heads as h, which is different from the latent frame height h. Our method computes a full attention map for downsampled versions of q and k, followed by binarization with minimal information loss. We downsample by averaging tokens in blocks of size n, which makes the reduced attention map computation n squared times more efficient than the full attention map. After obtaining the reduced attention map, we apply the softmax operation and compute the cumulative distribution function, CDF, for each row. We then binarize the map by keeping only values where the CDF exceeds the threshold of 1 minus THR, where THR is a parameter of the algorithm. This results in a unique sparsity pattern for each head, represented by an S divided by N by S divided by N matrix of binary values indicating whether to compute attention for the corresponding N by N block. We find that combining NABLA with Santa yields the best visual quality, leveraging both our method's adaptability and STA's strong prior mask. The STA mask is computed based on parameters such as the number of latent frames, height, width, and window parameters. The final mask for each data sample is a combination of the NABLA and STA masks. Once computed, This mask can be directly used in the flex attention algorithm to enhance training efficiency. In our fine-tuning experiments, we evaluate our method using the WAN 2.114 BT2I model at 720p resolution, focusing on self-attention blocks due to their significant contribution to overall computational load. We implement NABLA alongside Santa as our baseline sparse attention method, ensuring reproducibility with consistent hardware and software configurations. We perform knowledge distillation of the teacher model using mean squared error loss, initializing the student model with baseline weights and replacing all self-attention blocks with sparse attention. Detailed hyperparameter information is available in the appendix, along with our key findings. For human evaluation, we conducted a side-by-side comparison of video quality generated by the baseline and fine-tuned models. 50 participants evaluated 20 video pairs, comparing them based on prompt alignment, visual quality, and dynamics. Results show that NABLA maintains perceptual parity with the baseline, even at high sparsity. We used diverse text prompts for the evaluation, allowing users to watch the videos repeatedly and make informed decisions on which video they preferred. Section Summary. In this section, we present the NABLA training algorithm, which incorporates token reordering and a mask computation method for efficient multi-head self-attention. Our approach combines NABLA with Santa to enhance visual quality while maintaining computational efficiency, and we validate its effectiveness through fine-tuning experiments and human evaluations, demonstrating comparable perceptual quality to baseline models even at high sparsity. Section: Pre-training experiments. In this section, we explore the effectiveness of our method during pre-training by training a custom DIT-based 2B model in 3 stages. First, we perform text-to-image pre-training at a resolution of 256 by 256 pixels using full attention. Next, we conduct text-to-video pre-training at the same resolution with full attention. Finally, we carry out text-to-video pre-training at a higher resolution of 512 by 512 pixels, again using full attention and the NABLA method, which introduces 80% sparsity. We start the first stage from scratch, and each following stage uses the weights from the previous one. The first 2 stages are consistent across all our experiments. We compare the training and validation loss convergence between the 2 approaches in the 3rd stage. Our findings indicate that the NABLA model converges more effectively than the full attention model. Additionally, we note that each training iteration takes 10.9 seconds for the full attention model, while it only takes 7.5 seconds for the NABLA model, giving us a speedup of 1.46 times.